I'm a senior mechanical engineering student here at the University of Maryland, and today I'm going to tell you about my remote sensing project. So the purpose of this project was to design, develop, integrate, and test a field deployable LiDAR sensor. And the objectives of testing were to map an object on the UMD campus and then to resolve a 3D point cloud and mesh of the object. So the bench I chose to map is located on the south side of campus. The south side of the chapel has a garden of reflection and remembrance, which has multiple benches with a curvature that I thought would be interesting to map. Additionally, the ground around the bench was nominally flat, and it was the furthest bench from the road, which was important because I wanted to limit the light interference. One of the fundamental aspects of remote sensing are that you're able to obtain information about an object without the sensor being in direct contact with the object. However, remote sensing still requires some kind of interaction between the target and the sensor in order to acquire info. So the interaction between radiation and the object can be explained with the LiDAR equation, which relates received optical energy, or the photons received, to the transmitted optical energy. The radiation source emits light energy and photons, which propagate through the air until they reach the object. The backscattering of photons caused by the object is then detected by the receiver. This photon count is then collected, analyzed, and interpreted. So here's my field deployable LiDAR sensor. LiDAR, or light detection and ranging, requires active sensing, and active sensing occurs when self-generated radiation is used in the sensing process, allowing for more control of the system. Passive sensing occurs when naturally occurring radiation, such as sunlight, is used in the sensing process. The line laser is powered by the Raspberry Pi through USB port, and the camera is powered and interfaced with the Raspberry Pi. Instead of using the accelerometer chip, I decided to use the iPhone Compass app to obtain angle measurements. When deploying the sensor on the University of Maryland's campus, I used an Ethernet connection from the Raspberry Pi to my laptop, and I gained access to the Pi through the BNC server. Everything was superglued into place because of the 12-inch distance necessary between the laser source and the Pi camera. This is necessary for range measurements. So the LiDAR system is designed around computer vision and tracking algorithms, and geometric relations are used to determine range measurements. So the transmitter of the system is the red line laser, as seen here, and the receiver of the system is the Raspberry Pi camera. The receiver collects and detects return photons while minimizing background noise, while the transmitter provides laser pulses that emit protons. At the beginning of the semester, I was tasked with manipulating computer vision tracking techniques. Computer vision is an interdisciplinary field of study that deals with how computers can gain high-level understanding from digital images or videos. It is relevant to my remote sensing project because in order to calculate range measurements, the location of a laser point or line in the camera's field of view had to be determined. For both a point and line laser, the camera field of view widens as the distance increases, so the laser appears closer to the center at further distances. Theta was determined by calculating the number of pixels to the center of the image, multiplying by the radians per pixel, and adding a radian offset. The radians per pixel and radian offset were both experimentally determined in calibration. For both the point and line laser, a 6-inch increment was used for the calibration and range curve. A piece of paper was used in the path of the point laser, while a wall was used for calibration of the line laser. Specific color of the laser in the images. After calculating the pixel distance to the center at each of the 6 increment spots, I created a range plot. By changing the RPC and R0 values, I was able to fit my data to an analytical curve. So I decided to map one of my Converse All-Stars. So here you can see it taped to the wall, and this is me scanning it. Some key features of the shoe that I wanted to be able to see with 3D point cloud were possibly the laces,
and then also just the curved surface and the angle of the shoe on the wall. So here's just a closer view so you can see the angle of the shoe sitting on the wall and some of the way the fabric puffs out a little bit. So in the Raspberry Pi, using the color picker Python code and looking at an image from the data collection, I changed the HSV min and max values in order to isolate just that laser light line. So here's an example of that. And then going into PyCharm using the data generation code, I input the HSV values and the RO and RPC values from calibration and get out this 3D point cloud. PyCharm is not the easiest to work with trying to show the graph, so I also use MATLAB, and going into MATLAB, the only thing I needed to change in the 3D point cloud code was the name of the import. So as you can see from this 3D point cloud, the shoe itself and the angle of the shoe is pretty well preserved, as well as some of the points where the laces jut out. And then as for the wall stayed pretty straight with just a little bit of curvature due to the hysteresis of the camera. With calibration done, it was time to head back to the bench. So because my target was located in a garden, I had to be aware of the changes in elevation due to mulch, the noise added from vegetation close to the back and sides of the bench, and the limitations of the distance behind the bench. In order to effectively map all sides of the bench, I decided to separate the bench into 8 sections. So this is me setting up my sensor. Initially, I was using the VNC server and an Ethernet cable to connect. And then here I am aligning the line lasers so it is horizontal on the bench. My sensor is designed to scan up and down, and the line laser light is parallel to the ground. Some additional challenges were blocking out ambient floodlights from Memorial Chapel and keeping the tripod equidistant from the target on all 4 sides. To overcome these challenges, I hung my jacket to block out lights nearby, and I used a tape measure to record my distance to the target. An HSV mask or threshold was made for each side and section of scans. The HSV filter was applied in order to isolate the laser from ambient light. Then, using Python code, I applied the HSV upper and lower bounds and went through each row of pixels in each photo in order to pick out the shape of the laser light. Then, the distance to the target was found using the calibrated range curve. These values, along with angle measurements, gave the XYZ coordinates of the target. So then plugging this into MATLAB and adding together each of the sections. So for the front of the bench, as you can see here, there are different offsets for each of the 3 sections that I took for the front of the bench. And as you can see, they're vertically concatenated and then mapped with the 3D plot. And then for the back of the bench, same thing applies with a few rotations about the y-axis or x-axis, and same for the left and right sides of the bench. So then for the final MATLAB code, basically I loaded all of those files together and plotted them on one plot. So this is the front of the bench, and it was made up of 3 separate data collections of the left side, the middle, and then the right side. And then they were added together into the 3D point cloud. And then for the back of the bench, the same 3 sections were applied, left, middle, and right. And you can see it's been flipped about the z-axis, so it's slightly different. And then for the left and right sides, not a lot of data was able to be collected because of the lights behind Memorial Chapel, but you can still kind of see part of the profile of the side of the bench. So then this is the full 3D point cloud representation of the bench, and all 4 sides were added together separately and then added together into this representation. So after applying some thresholds in MATLAB, I was able to get this as my final 3D point cloud in MATLAB. I then imported that into Cloud Compare in order to get a mesh. However, there were difficulties in constructing surfaces and filtering, so I went back to the unfiltered one. I then applied a noise filter on the 3D point cloud that included the ground, and this was able to actually get rid of some of the extraneous points as well as lower the density of my point cloud. Then I used segmentation in order to filter out unwanted points, and as you can see here, I'm just going through and deleting those extraneous points. So my first attempt at a mesh was using the 2D Delaunay triangulation, and this actually gave a pretty good shaped bench. I was pretty happy with this, but I wanted to try to do the Poisson surface reconstruction as was suggested to use in MeshLab. So here's my Poisson surface reconstruction. In order to get this, I computed the normals first. As you can clearly see here from my mesh as well as from the 3D point cloud, I was not able to pick up almost any points on the seat of the bench, and this really affected whether or not I was able to get a full 3D model. The gap ended up making this difficult. However, the angle that I was able to collect data at allowed me to pick up the 2 front legs of the bench, which I would not have been able to do if I had been angling down in order to try to get the seat. And overall, I was pretty happy with how much of the curvature I was able to pick up.